So when that happens, so this is our point A, right? When we remove the support, because of temperature increase, what will happen? The thing will expand, right? So that is here's our point A. Our point A is still there, right? So now we have our B prime. Okay. So the B prime, this is what we call our deflection due to temperature. Okay. So delta T is equal to alpha change in temperature multiplied by original length. So this is our original length. Okay, that's original length. So in reality, right, point A and point B will not change in dimension. It's fixed down there. We are doing it because we want to determine the stresses. Okay, so for point B prime to go back to B, right, to go back to B, okay, so from B prime to push it back to B, you need a what? You need a load. You need a force. And this force has to push it back, right? And that force is our redundant load. I call this our RB there. Okay. And how much to push back? This is what we call our delta R. Okay. So to find out our delta R, now it's mechanical loading. Okay, is minus RB. Okay, L naught over AE. Okay. So now, what did I tell you all? Temperature increase, compression. Now, because the stress in AB is equal to minus RB divided by area, it's in compression. Okay. Now we can see that, right? Right. Now we can see. Now the next thing is, what if now, okay, we go into, it's almost, I think we got him put up the mission accomplished banner. You guys are cheeky sort. Okay, so now we look at temperature decrease. Okay, we look at temperature decrease. So I'm going to put this side by side. Okay, so the next case we're going to do a temperature decrease. Okay, temperature decrease. So where, as I said, stress AB will be in tensile. Okay, no doubt the length is going smaller. Okay, so the same thing. Okay, so the same configuration. Now it goes opposite. Okay, so I think I can copy this. Okay, remove the support at B as you go do the same. Okay. Now we have this now. Okay. So now we were to remove the support at point B. Okay, we do the same thing, exactly the same thing. We do the same thing. We remove the support at point B. Okay, so point A is still there. We remove. So when we start to remove the support at point B, because it's cold, right? It contracts. The change in length gets smaller now. Okay. So the motion from here to here, right? This is now our delta T. Right? It's string, it gone smaller. It's cold now. So we also know that you have to push it back to its original position. So this is A. So we have to now pull it back. Okay, so we have to pull it back. I'm just thinking which one to copy. Okay, I'll copy this one. So we have to pull it back to its original position. Okay, and this is, I'll call it RB again. Okay, and this is your delta P or delta R. Okay, and then for this case, delta R is equal to, now it's going to be in what? Tension now. Okay, minus by multiply L naught over AE. Okay, so that is why, because of RV over here is in tensile, stress AB is equal to positive RB divided by area. So that is why this is in what? Tensile. Okay, I hope this will help you understanding why decrease in temperature will be tensile, increase in temperature compression. Would this be considered shortening? Yeah, when it's cold, it reduces in length. Okay, and then there are two formulas that I've written down here that we have seen. Okay, so the first formula that I've written down that first time that you have seen is delta T is equal to alpha multiplied by change in temperature L naught. Okay, so alpha is the thermal expansion coefficient. Okay, and the units is per degree C. Okay, and then the delta T is the T1 minus by T naught. Okay, and L naught is the original length. Okay, so this is the first time you have seen this formula. And the other thing, the other thing to take note, okay, we still have to apply how I wish I've written with space into consideration. The other thing that we have to apply, okay, is still important, is the deflection due to the temperature plus by deflection due to the redundant load must be equal to 0. So nothing changes. Everything is still the same with mechanical loading. Okay, right. So we are going to look into the next example. The next example is one of the most complex example. Okay, that you have seen in this thermal expansion or contraction. Okay, so just to quickly summarize. Okay, just to quickly summarize is when you restrict motion, okay, then you get stress. When it's allowed to move, no stress. I repeat again, when it's allowed to move, no stress. When it's restricted of motion, then you get stresses induced by the heat. Then when the temperature increases, you get compression. When temperature decreases, you get tensile. Okay, so the next problem, example number 2. Okay, you can get all this from your notes. Not notes, but I posted them. Okay, so example number 2.
Sorry.
Yes.
Do you mind just quickly going to the previous page? I just want to get the last
Okay, no problem. Sorry, I did not. I should have given you some time on this. Anyone? Any question, please?
When you spoke about the part that said when it's allowed to move and when it's not allowed to move, you're referring to the pin and roller, right?
Yes. When you allow motion or you don't allow motion, it can be one end that is built in, the other one is on a roller. You allow it to move. If both are built in, you're not allowed to move. Wait. When the temperature decrease, yes, it's tensile because the compressive stress is decreasing. No, Jordan, no. When temperature decrease, right? When you allow motion, right? The structure decrease in length, right? But in real life, right? The change in real life, point B is always there holding the structure. Okay, point B is always there. We remove it is because we are going to analyze the structure. Okay, so point B is always holding. So the structure want to go smaller due to heat, right? Point B is always holding. So it has to pull what? It has to pull back. That's why it's in what? In tensile. Jordan, is that clear?
Sure.
Okay. Resilience. Okay, you can, yeah, resistance. Okay.
So sorry, we're talking growth, expansion in the axial direction. What about the radial? Isn't there implications too for temperature?
So usually when temperature increases, there's a expansion, right? Like the situation on the left, right? When I remove the support at B, it grows, right? But in reality, B is down there restricting it. So to restrict it, you have to push it back.
No, I'm saying that isn't there a radial expansion as well?
Okay, so we are talking about lateral and transverse.
Axial.
The
Yeah.
transverse is very small for this case, okay?
Okay.
Okay. So even for this case that you see now, the transverse direction, as in the y direction, there's no restriction, Andre. So when there's no restriction, yeah,
No stress.
yeah, there's no stress. Okpara, you're trying to speak. Are you okay?
Yes, thanks.
Yeah, okay now? Okay.
Thank you.
Right. So we are going to look into our last example. I think I'll finish class in like 12:15. But you have to go, you have to go. Okay. I don't want to hold you back because all these are recorded anyway. Okay. The only thing advantage of staying behind is when you don't understand, you ask, someone can speak back to you. Okay. So this is the example. And this is not 6, this is 0. Can you change that? My bad. Okay, it's not 16 times 10 to the power minus 6 is 0. Okay. So at room temperature, a 0.5 millimeter gap exists. Okay, the gap exists. At the later temperature, when the temperature has reached 140, determine the normal stresses in the aluminum and the change in length of the aluminum rod. Okay. So given below are the cross-sectional area, Young's modulus, and alpha coefficient of thermal expansion. Yeah, if you have to leave, you have to leave. Okay, as I said, all these are recorded. Okay, the only thing advantage of staying behind is when you have a question, you ask me, I'm here to answer. Okay, and I'm going to take my time. I'm not going to rush over this. Okay, usually when I rush, yeah, the only person that lose when I rush is students. It's your understanding. I'm not going to do that. I'm going to take my time. Okay, so we know for the first thing is the original temperature, the ambient temperature, the T0 is at 20 degrees C. Okay, and then the T1 is equal to 140 degrees C. Okay, so the change in temperature, the general formula is the new temperature minus the original temperature, which is 20. So this is equal to 140 minus 20. So it's positive 120 degrees C. Okay. Now this question is a bit tricky. Why is it tricky? It says that there's a gap. Okay, there's a gap. So I want you to like we do interactive thinking. If this structure, the original temperature is 20 degrees and the final temperature is minus 200 degrees,